to this video. My name is the Solution Key, and we are going to solve these problems. Watch in HD. What is equilibrium? Equilibrium is the state in which the sum of the forces is 0 newtons. That is it. Number 2, what are the two physical situations in which an object is in equilibrium? Well, one would be if the object, or not if, but let's just say, the first physical situation where total force is 0 is when the object is at rest. The second is when the object is moving, but it can't be moving in any, there's a specific type of motion. It has to be moving at constant velocity. Constant V. When the resultant force is 0, what can be said about the x direction forces and the y direction forces? Well, if an object here feels all of these different forces, some are x, some are y, maybe there's a force over 2D, so that has an x and a y part, and maybe a second force to the left. What we know is that all of the x forces cancel, and all of the y forces cancel. In other words, we know that the total x force is 0, and the total y force is 0. So what do the answers say? The x direction forces are balanced, and the y direction forces could be unbalanced. No, because then there would be a net force in the y direction, and the total resultant force would not be 0. So this is wrong. B says that the x direction forces are balanced and the y direction forces are balanced. Yes, that is correct. And we know the others are wrong, but you can read them to confirm. Number 4. A 16 kilogram block is being moved at constant horizontal velocity, underline that, along a flat, rough surface. Rough means we are going to have some friction. A person is pulling with 138 newtons directed along this angle, and we have to first draw a diagram, force diagram. I'm going to make mine a free body diagram with just a dot. The person pulls at this angle with 138. What is the angle? It's 49 degrees. Gravity pulls down. It's 16 kilograms. So 16 times 9.8 mg, that's the value of the weight, the force of gravity. The normal force is up, we know. And look, we're going to have to find it. And then the other thing we have is friction, because it's a rough surface. And for this thing to move at a constant velocity, there has to be something pulling to the left, balancing out this 138 force. So the 138 newtons has, I'm going to take away my angle because it's going to get a little sloppy here. The 138 force has an x part, or an x component, and a y part, or a y component. The x part is 138 times the cosine of the angle 49. The y part is 138 times the sine of the theta, like that. And since I've drawn the components in, I can put a little squiggle over the 2D force, because I've already considered it. There's step A. Step B, find the normal force. The normal force is a y direction force, so we should use the equilibrium condition that the forces balance. So what are the up forces? We have the normal force, and then we also have 138 newtons times sine 49. And what are the y forces we have? We have 16 times 9.8. I'll go ahead and plug that in, and it's 156.8. 156.8 newtons. Let's see. And I'm out of room to draw the newtons. I can't just move these over, can I? And so we can solve for the normal force by subtracting 138 sine 49 from both sides. And what do we get? 138 sine 49 is what we subtract. And we 53 about, 52.6 something. So we'll call it 53 is the normal force. 53, there we go. C says find the friction force. We know that the left forces balance the right forces, so they are equal. They are balanced. It's being pulled to the left with as much force as it is to the right. So the friction force equals, that's the only left force, is friction. The only right arrow is 138 cosine 49. So you plug this into the calculator, 138 cosine 49, and you get 91 newtons. There we go. Okay, the next problem says we have a 25 kilogram block being moved at constant horizontal velocity. That is important. So let's underline that. Constant horizontal velocity. That tells us that the total force, the sum of the forces, the resultant, is 0. And it's going to the right on a rough surface, flat. Rough tells us there's friction. A person is pulling the block with the force F applied, directed along an angle theta, up from horizontal right. So here's what that F applied looks like, along some angle theta. The normal force is 125 newtons. The friction force is 106 newtons. We know friction opposes the motion, 106 newtons. And that's all we're told. That's all we're told. Step A is to draw a force diagram. My force diagram is just showing the block as this dot, and because it's only the block alone, free, that makes it a free body diagram. And the only other force I need to add is gravity, which pulls down. Gravity is down. And what's the value of gravity? It's mg. Right. To find the applied force, we're going to first have to find its x component and its y component. Okay. So what will we use to find the x component? We will use the equilibrium condition. The left forces equal the right forces. Since the block has constant velocity, it's not accelerating, so it doesn't feel any resultant x force. So what are the left forces? There's just that 106 newtons of friction. What are the right forces? Just F sub x. Like that. Okay, so now we just found, check, we found the x component. Now let's find the y component. We'll find it using the equilibrium condition in the y direction, which tells us there's balancing of the forces on the y-axis. The up forces are equal to the down forces. So what goes into the up forces? Well, there's the 125 newtons, and then there's the y component of the applied force. The down forces are just mg. The mass is 25. G is 9.8. If we subtract 125 from both sides, what do we get? 9.8 times 25 minus 125. This is 120 newtons. Did I do that right? Yes, I did. 120 newtons. So now that we know the two legs of this right triangle, right? This right here is a right triangle. The hypotenuse is the applied force. So how do I find the applied force? I use the Pythagorean theorem. It's going to be the x leg, 106 squared, plus the y leg squared, all square rooted. And what do I get for my applied force? Plus the 106 squared, and I have to square root everything. I get about 160 newtons. That's part B. Then for theta, I have to use inverse tangent. The y leg, right? Look at the angle here. Look back at your angle. the opposite is Fy, which you found to be 120. And the adjacent is Fx. That's adjacent to the angle, which is 106. So you do inverse tangent of 120 over 106, and you get 49 degrees. Good. The next question, and that's part C right there. And we don't really have to say up from horizontal right, because it was given in the problem. So we're really done. The next says, a horizontal rope is attached to a wall as shown below. A person is pulling on the rope to the right so that the rope is taut. That means there's tension in the rope. So this means tension is in the rope. What can be said about the two ends? Okay, well, here's one end, here's the other end. The person is pulling to the right, which means the rope is taut, there's tension, and that means that this end wants to get pulled back to the middle. And let me draw those forces as equal. So the person is pulling, which means this end on the right side wants to resist it resists the stretch, it wants to be pulled back to the left. That force pulling the rope back to the left, that force that resists stretching, is tension. And on the right side, on the left side here, that end is also getting pulled and stretched because the entire rope is being stretched. And so this end opposes the same stretching. This end also wants to go back to the center. In fact, if you were to cut with scissors, if you were to cut this with scissors, is that what scissors look like? Kind of. Then the rope would go springing over to the right. So we know that this left end is also feeling some pull, because if we let it go, if we released it from the wall, it would go moving to the right. It's being stretched, it resists that stretch, and the force that resists the stretch is tension. These values of tension are equal to each other because the tension is distributed evenly in the rope. That's just a property of the ropes that we're dealing with here in these problems. So, what's the problem say? The tension, look at number I, letter I. Tension pulls the left end, that's this end over here, to the right. Yes, that is true. And then II says tension pulls the right end, that's over here, of the rope to the left, toward the center. Yes, that is also true. Both ends want to be restored back to their non-stretched position. So, what's true? C. C is the correct answer because both I and